Section 7.7. Implementing our functions. When you're doing a top-down design, as we just did, you start with your overall problem and break it into subproblems. That's why we started with spell check, our overall problem, and eventually reached functions such as addLetter, which didn't need any further splitting. But when we ask Copilot to implement these functions, we're not going to work in the same order. Rather, we're going to work in the opposite order, doing the smallest subproblems first, then moving on to the functions that depend on those subproblems. This corresponds to moving from right to left in a figure such as figure 7.4, starting with leaf functions and continuing to non-leaf functions. We implement functions in the opposite order like this, so that Copilot knows about the smaller functions by the time we want to implement larger functions. That way, Copilot will be more likely to call our subtask functions as desired. We want to stay squarely focused on problem decomposition here, and we've made some decisions toward that end. First, while we'll include some tests in our docstrings, we won't be pursuing full testing in this example as we would have done in Chapter 6. We encourage you to use DocTest to run the tests that we do provide, as well as add your own tests for further confidence in the code. Second, we haven't dwelled much on our prompt engineering, instead focusing on the prompts that yielded good results. In the next chapter, we'll focus on debugging, and that's where we'll return to prompt engineering. Third, we're not focusing on reading and understanding the code in full detail. That said, we've included some annotations to explain what the code is doing and how it works. Section 7.7.1. Create word list. We'll start with our create word list function. As in Chapter 3, we write the function header, the def line, and the docstring, and Copilot fills in the code. This is how we'll have Copilot write the code for all the functions in this chapter. We already know what our create word list function is supposed to do. Read the words from the word list file and return them as a Python list of words. We carefully write what we want in the docstring, as shown in Listing 7.1.
Listing 7.1. Function to read the list of words.
We've used a descriptive parameter name, file name, which gives a good clue to the purpose of the parameter. We've also been careful to use this parameter name in the docstring. Our docstring also makes it explicit that we want to return the list, rather than say print it. We haven't included a test in the docstring for this function, and that's because we didn't want to distract from the overall goal of implementing each of our functions. If you wanted to, though, you know how. Specifically, we did this in Chapter 6 where we created a small file for purposes of testing. Here, you could create a small file with one word per line but with only a few English words, and then test that the list of words we read from the file matches the words that we put in the file. We're finished with our create word list function, so we can mark it as complete as in Figure 7.5.
Figure 7.5. Full functions diagram with create word list finished.
To save space, we won't show the updated figure after we implement each function, but we'll show it occasionally. Section 7.7.2. addLetter. Now we'll work on the functions that all possible words needs, starting with addLetter. The addLetter function takes a string as a parameter and returns the list of potential words that can be formed by adding one letter to that string. Let's think briefly about what to expect from this function with a quick example. If we gave the function the string cu, as in Table 7.2, it's going to generate a list of words with every letter added to each possible position. This means it should include strings that have an A added before cu to make ACU, a B added before cu to make BCU, and so forth for the character before cu stopping with ZCU. The function should also include every letter in between C and U to form CAU, CBU, CCU, and so on to CZU. Lastly, as there are 3 possible positions to add a letter, we'd expect the function to add every possible letter after CU to form CUA, CUB, CUC, and so on until CUZ. Our prompt to Copilot and the code generated by Copilot is shown in Listing 7.2.
Listing 7.2. Function to add any possible letter.
The code here is quite subtle and deserves careful testing. For example, notice that the outer loop uses len of word +1, rather than the more standard len of word. Without the +1, we would add characters at each existing index of the word string. But that would actually miss the fact that we also want to be able to add letters past the existing letters. The +1 adds one extra iteration where we add a character to the end of the string. For each index of the outer loop, we consider each possible lowercase letter in the inner loop. The line new word equals word of : I, plus C plus word of I colon uses string slicing, the technique of extracting letters out of a string using two indices, to add the current inner loop character to the current outer loop position. Although we aren't spending much time on testing in this chapter because the focus is problem decomposition, you would want to test this function by giving it a single misspelled word, that is CU, and then printing the returned words and ensuring it includes strings such as ACU, add at the start, CAU, add in the middle, and CUA, add at the end, as well as possible real words such as cup and cut. Note that we wouldn't want to include exact tests in the docstring because the lists returned by this function are huge. For example, try typing this at the Python prompt.
See this code?
You'll get a list with 78 strings in it, and that's for our tiny CU string. The number of strings returned in the list grows significantly as we increase the number of characters in the parameter string. Section 7.7.3. Delete letter. Like add letter, delete letter takes a string as a parameter and returns a list of potential words. The difference is that rather than adding a letter, delete letter deletes each possible letter from the string to arrive at new possible words. Let's think about what we expect this function to do. If we give it the string carf, it should try deleting each letter to produce the strings arf by deleting C, crf by deleting A, caf by deleting R, and car by deleting F. Again, we gave the prompt to Copilot for this function, as shown in listing 7.3.
Listing 7.3. Function to delete any letter.
This code is similar to our code for add letter. One difference is that we have only one loop this time, not two. The reason is that we don't need an inner loop to loop through the letters A, B, C, D, and so on. That's because we're deleting letters that already exist in the word, rather than figuring out which letter to add. Section 7.7.4. Change letter. Now it's time for our third and final subtask of all possible words : change letter. This function is responsible for generating words where one letter in the string is changed to some other letter. In thinking about what we'd like to see happen here, let's consider the string CU again, as in table 7.2. We want this function to replace the letter C with all possible letters to create the strings AU, BU, DU, and so on until ZU, and to replace the letter U with all possible letters to create the strings CA, CB, CC, and so on until CZ. Note that we omit trying CU as that's the initial string. We only consider changes to letters. See listing 7.4 for our prompt and the code from Copilot.
Listing 7.4. Function to change any letter.
This code is quite similar to our add letter code. The main difference is that we use string slicing not to add a new character, but to change an existing character. At this point, we've completed the three functions we need to implement all possible words. Check out figure 7.6, where we've marked off the substantial progress that we've made. We'll next tackle all possible words.
Figure 7.6. Full functions diagram with all possible words helper functions finished.
Section 7.7.5. All possible words. The reason we can now implement all possible words is that we've already implemented the three subtask functions that all possible words needs to do its job. When we ask Copilot to write this code, we're expecting to see calls of add letter, delete letter, and change letter. Take a look at listing 7.5, and you'll see Copilot doing exactly this with the prompt we've given it.
Listing 7.5. Function to generate all possible words.
Generating all possible words is no easy feat. Yet, we've managed to do it with a single line of Python code here. It just calls to three helper functions and that's it. This is exactly why we're doing top-down design. To make complex functions much easier to implement by offloading much of their complexity to helper functions. Section 7.7.6. All real words. We're close to being able to implement get spelling suggestions, but not quite, because we first need to implement its subtask function all real words. The all real words function takes two parameters. The first parameter is the English word list. This will come from an English word list file. The second parameter is the list of possible words. This will come from all possible words. The function returns the list of possible words that are real words. Let's do this.
Listing 7.6. Function to generate all real words.
The test in the docstring is a good example of how this function works. It's using the English words list for the first parameter, and the possible words list as the second parameter. The function will return those words from possible words that are also in English words. We're using this very small test case, rather than using thousands of English words, because this makes it much easier for us to determine by hand what the correct return value should be. Let's check how well we're progressing in figure 7.7. We're getting close. Just 2 functions to go.
Figure 7.7. Full functions diagram with all possible words and all real words finished.
Section 7.7.7. Get spelling suggestions. We've implemented create word list all possible words and all real words, and those are the only 3 subtask functions that get spelling suggestions needs. That means it's time for us to implement get spelling suggestions. This function takes 2 parameters: the name of a file that contains real words, 1 word per line, and the string that we want to provide suggestions for. It returns the list of the unique suggestions. As always, when scrutinizing Copilot code for a non-leaf function, you want to check that it's calling the helper functions that you expect it to be calling, as shown in listing 7.7. Before you move on, convince yourself that it's calling all the helper functions that it should be calling.
Listing 7.7. Function to return spelling suggestions.
That last line there is tricky. Apparently it's ensuring that we return only unique words. But how? Let's ask Copilot to explain. Here's the explanation that we got when we used the /explain command to Copilot. Copilot, this line of Python code is performing 2 operations. 1. Set of real words. This is creating a set from the real words list. A set in Python is an unordered collection of unique elements. So this operation is removing any duplicate elements from the real words list. 2. List of set of real words. This is converting the set back into a list. The result is a list where all elements are unique. So, in summary, this line of code is removing any duplicate words from the real words list. Section 7.7.8. Spell check. We've made it to our final function, spell check. It takes 1 parameter, a string indicating the name of a word list file. It asks the user to type a string, and then shows the user all spelling corrections for that string.
Listing 7.8. Our main function that interacts with the user.
Consult figure 7.8 to see that we have indeed implemented all of our functions.
Figure 7.8. Full functions diagram with all functions complete.
You need to add 1 line of code at the bottom of your Python program to actually call this function. Otherwise, your program won't do anything because no function is being called. So add this line at the bottom.
See this code?
Now, assuming that you have the wordlist.txt file in your directory along with your Python program, you can run it. It will ask you to type a word. Try typing the misspelled word successful, the word that started it all, and you should see the program provide the spelling suggestion of successful like this.
See this code?
Try other misspelled words too, such as thorough and acceptable. With these misspelled words so far, our program is replying with only a single spelling suggestion because there is only 1 real word a single edit away from the words we're trying. We encourage you to try entering the word carf to see that our program can provide many possible spelling suggestions. Congratulations! You've completed your first real-world top-down design. Your program provides spelling suggestions for a word, much as a spell checker does. We made the problem considerably easier to implement by doing some upfront design work to break down the original problem into smaller subproblems. Many computer scientists view problem decomposition as the most critical skill needed to write good software. We saw the value of problem decomposition in this chapter. It made a large problem solvable by breaking it into smaller steps until each step was easier to solve. We applied this skill in this chapter using top-down design. Start with the large task and break it into smaller tasks, to put it in practice. This skill remains critical when working with tools such as Copilot and ChatGPT, because they perform better when solving small, well-defined problems compared to large problems. As mentioned at the beginning of the chapter, problem decomposition is more of an art than a science, and it takes practice to get it right. We'll do more problem decomposition in our upcoming chapters to help give you more intuition into how to approach it yourself.